Good evening, all. I am Abdul Conte. I'm doing this presentation for the ECE 606 Advanced Data Analytics in Smart Grid Homework 2. The title of the paper that I'm doing this presentation is Power Quality Disturbance Classification with Optimized S Transform and Kernel SVM. This work is based on the publication of TanQ and others and is published in IEEE Transaction on Industrial Electronics. Background: power quality disturbance arises from nonlinear loads, renewable energy sources, and EV chargers. The common power quality disturbance include sag, swell, flickers, transient, harmonics, etc. Power quality disturbance identification is critical for reliability and power system protection. Traditional time frequency analysis struggle with mixed disturbance and noise. This figure in the background shows the normal versus disturb for EV, solar, and power electronics. Problem statement. The need for robust classification of a single mix and nonlinear mix power quality disturbance on a noise. The conventional time frequency resolutions fail when spectral features overlap. The goal is a supervised learning model that remains accurate on a noise and support real-time application. This figure shows the blue. This plot in the background shows the blue is the single power quality disturbance, which is kind of clean spectral peak, easily separable. And then the orange is a mix of the power quality disturbance overlapping peaks from two sources. And then the red in the plot shows like the nonlinear mixed power quality disturbance, multiple blended peak with added noise, which is very hard to classify. The analytical technique or the unique approach used. The optimized S transform. They tunes the window width for maximum energy, the concentration, high time frequency clarity. And then the kernel SVM combines multiple kernel types, the RBF, the polynomial for feature fusion. And then also the integrated OST, which is like the end-to-end framework for extracting features plus classification pipelines. The data set. This work was simulated in a MATLAB power quality data set. You can see some of the parameters here they use, like the sample per disturbance, which is 2000, and a frequency of 50 hertz. The model architecture. The diagram in this diagram shows the model architecture in which the authors used to carry out the work. The features extraction like the OST, spectrogram, statistical and energy feature, the classifier, which is the kernel, the SVM with mixed key other data set, and also the parameter optimization like the grid chart and then the cross validation. The result noise robustness. The bar chart visualization comparing model performance on a different noise level. For the OSTM to the KSVM consistently outperform other models, achieving greater than 99% accuracy above 30 decibel and maintaining also greater than 97% at 20 decibel. This the results show it improve upon traditional S transform plus the SVM by roughly 3 to 5%. And also the real-time processing remain visible, which is approximately 200 milliseconds per sample. This slide shows the results, the mix and the nonlinear power quality disturbance. Take a look at the visual plot here shown. The top left is an example of a mixed power quality disturbance transient plus swell. And also the top right is an example of the nonlinear power quality disturbance, the distorted waveform. The bottom left is the comparison table of the OST and the KSVM which kind of like outperform the traditional model greater than 97.5 versus less than 90%. The bottom right is the confusion matrix, which is a near perfect classification performance. The result model comparison. The OST and the KSVM is kind of like 99.2% accuracy, which is high robustness. And then for the VMD plus the DT, which is 93.8%, which is moderate robustness. The DVT plus the SVM, which is 91.5%, which is low robustness, and then the remaining, which is like the music, which we say like the music ESVM, which is 95.7% moderate robustness. What is like the utility implication? It's kind of like enable accurate power quality monitoring in real time. It supports alarm, data logging, and analysis. It's also scalable to substation power quality sensors. The limitation and feature work. The OST actually increased the computational cost, and it also need validation on real data sets. Summary and references. The supervised learning, which is the SVM, classify complex power quality disturbance. The OST improved the spectral clarity and accuracy, and also high performance for mixed and noisy power quality disturbance. And it's also practical for utility power quality monitoring. This work was published by Tanq and others in IEEE publication.